Hello, I am Professor Sankaran in the Department of Metallurgical and Materials Engineering. Since sigma ij prime is a second rank tensor, which already we have stated, it has a principal axis. The principal stress deviator are the roots of the cubic equation. This also we know. We have looked at stress and then strain. Now it's a stress deviator because these are all tensorial quantities. So nothing new to us. So here instead of I1, I2, I3, here it is J1, J2, J3 are invariants of the deviator stress tensor, and J1 is simply this, and J2 is this, right. This is a principal, some of the principal minors that we have already seen, and J3 is the determinant. Sorry, let me go back. Yeah, J3 is the determinant, total determinant. So, so these particular invariant I am showing because some of the yielding theories, right. So we will be looking at several theories, yielding theories. So some of the yielding theories will directly note, I mean they will simply quote this J2 invariant, J1 invariant. No, that time if you are not familiar with this, then it is a little confusing. So now that you know, J2 is a invariant of the stress deviator matrix, that we know. So J1 is known. So once you remember all these three equations and their invariants, then it is very easy to appreciate later on. Okay. So we have spent considerable time on the description of the stress and description of the strain and some important I would say the properties of these tensors and their parameters, right. Now we will slowly get into relations between stress, elastic stress and elastic strain. Please remember, we are looking at only small strains and which is purely elastics, right. So when we say elastic deformation, then it can be compression as well as tension. So you take these two examples. This is an initial shape of the member body and which is being subjected to tensile deformation. That means the length increases, the width decreases. Similarly, this member is subjected to compression, then the length decreases, the height increases. So that is something normally we expect. This is in a pure elastic deformation. So if we want to relate a stress tensor to the strain tensor, we must introduce material properties. The equation of this nature are called constitutive equations. Equations of this nature are called constitutive relations or constitutive equations. So what is this constitution equation we are familiar with? This is well known, Hooke's law. Sigma x is equal to E times xn. So this is a linear elastic deformation. So E is the material property, which is modulus of elasticity in tension or compression in a linear fashion. So the transverse strain has been found by experience to be a constant fraction of the strain in the longitudinal direction. This is known as Poisson's ratio. Okay. So this means you can express this epsilon y is equal to epsilon z is equal to minus mu times epsilon x, right, or it can be related to the stress, which is also can be related to minus mu. The epsilon x can be written as sigma x by E, right. So, this is a simple relation. First time we are writing a relation between a strain versus stress in a linear. For most metal, mu is 0.33. So, this is for a single dimension. So, if you are interested in developing this relation for the 3D state of stress, and then we should consider a similar cube where we have just looked at for description of a stress at a point. Similar geometry you can imagine where all the normal stresses sigma x, sigma y and sigma z and shear stresses were marked. Okay. So, and before we get into the relation of the stress strain in a 3D state of stress, there are some assumptions. What are the assumptions? Because the elastic stresses are small and the material is isotropic, very important, right? You have to pay attention to these details. If these are the conditions, if the material is isotropic and the elastic stresses are small, then we can assume sigma x does not produce a shear strain on the x, y and z planes, and tau xy does not produce normal strains on x, y and z planes. We can apply principle of superposition. So, under this conditions, the sigma x will not have influence on shear strain and the shear strain will not have influence on normal strain. Then we can use a principle of superposition. So, what is that? So, this is a table 3 by 3 matrix you can create using similar what we have just written there. For a stress in x direction sigma x, we can write a strain in x direction epsilon x, which is sigma x by E. But the strain in y direction can be written epsilon y is equal to minus mu times sigma x by E. This is epsilon z is equal to minus mu sigma x by E. So, what does it mean? We are now looking at the effect of stress in the x direction, but what its effect on or what kind of strain it will produce in y direction and z direction can be expressed with the simple relation. That is what you have to look at it. Okay. Similarly, you look at the strain, the stress is x normal stress, that is sigma y is a normal stress in y direction. The strain in y direction is simply given by sigma y by E, but the effect of this on x direction, that is if you want to see what kind of epsilon x it will produce or what kind of epsilon z it will produce just by the normal stress which is acting in y direction, then we get this kind of relation. So, that is the beauty of this superposition of the strain components in the x, y, z directions. So, we can just simply write like this. So, whatever I have just put in the table, you can just write it like this: epsilon x is equal to 1 by E sigma x minus mu times sigma y plus sigma z, right. So, that is what it is. So, so these kind of relations can be written for 3 axes. So, this is called a generalized Hooke's law, right. This is called a generalized Hooke's law. It is, that means the stress strain relation in 3 dimension. So, The shearing stresses acting on the cube produce, that is tau xy is equal to g times gamma xy, shear stress and shear strain, and this is g is a shear modulus. Similarly, in yz and xz directions. Okay. So you have three constants now: E Young's modulus, G shear modulus, mu is Poisson's ratio. These are the constants involved in the stress strain relations for isotropic elastic solids. Please understand, this is very important. These relationships are fully valid for isotropic elastic solids. And then we can now look at the other relationship where these elastic constants have. Another constant, volumetric modulus of elasticity. What is that? So, which is K. So, sigma m is mean stress we know, sigma m by delta, delta also we know, which is also equal to minus P by delta, which is equal to 1 by beta. What is this? Where minus P is a hydrostatic pressure and beta is the compressibility. So, these are some general relations these stress strain components have. So, we can just try to put this into perspective, how we can write this. Again, another relationship, you have K can be related like this, and then it basically what we are trying to see is we are trying to give another relation for volumetric modulus, which can also be written like this. K is equal to sigma m by delta is equal to E by 3 times 1 minus 2 nu. So, all these relations will be handy if you try to solve some small problems in the area of elasticity. We will try to use it when it comes, especially in fracture problems and fracture mechanics, for example. Look at some of the the stress and strain states, and we will be using all these relations. So, another important relationship is the expression relating Young's modulus, shear modulus and nu is G is equal to E by 2 times 1 plus nu. These are all some standard relations. Okay, so now I am coming to another important topic, or I would say we are looking at fundamentals. So, I am introducing another terminologies, plane strain and plane stress. So far we have looked at a strain in one dimension, strain in 3 dimensions, stress in 1 dimension, stress in 3 dimensions, but we did not talk about a plane strain or a plane stress. So, the question is, why do we do that? The problem is, most of the engineering problems are in a practical situations becomes too complex, right? So, if you make it a three dimensional problem and reduce it to what, if you reduce 1 dimension, the mathematical treatment can be simpler. You can try to solve completely. That is the primary reason. So, the many problems can be approximated by 2-dimensional approach by assuming that the stress or the strain varies only in a single plane, usually in xy plane. Okay. There are 2 ways to create such approximations by assuming that the force normal to the plane is 0. The plane strain, this is called plane strain assumption. If you assume that the force normal to the plane is 0, this is plane strain assumption. The 2 approximations, we shall continue, or we shall outline the plane stress type of analysis first. Okay. We simply take equation of generalized Hooke's law and put sigma x is equal to 0. Then we have just developed 3 equations as a generalized Hooke's law, where you put simply sigma x equal to 0. then we get these equations, right. So, I have shown 3 equations, and if you just plug in sigma x equal to 0, then you will have this set of equation. This is valid for, sorry, this is a plane stress type equation. So, this is exactly for shear strain. So, 0 force in the z direction implies these two components become 0. Therefore, only the first of the two equation is non-trivial. So, this is a condition for the plane strain problems. Sorry, plane stress problems. These two equations, what we have shown is a plane stress formulation. For a plane strain analysis, is a little more complex. By putting epsilon z is equal to 0, the Hooke's law gives an expression for sigma x is this, and this can be substituted in the first two equations of the generalized Hooke's law involving sigma x and sigma y only. Then this equation becomes like this. So, it looks a little complex, but actually it is not. If you just plug in these values there, then you yourself will find out that this is simple to manipulate. But what is important is the new terms which will emerge. That is what you have to focus. By just that is why this plane strain analysis is a bit complex. But you can just appreciate by looking at these expressions, right. So, just plug in this assumptions into this, and then you will get finally this expression epsilon x equal to 1 minus nu square by E times sigma x minus mu by 1 minus nu times sigma y. We can simplify this. We can define a new parameter called plane strain modulus, that is E prime. That is E prime is equal to E divided by 1 minus mu prime square, okay. And a quantity mu prime such as mu prime is equal to mu by 1 minus nu. Then we can write the above equation as epsilon x is equal to 1 by E prime times sigma x minus mu prime sigma y. Sigma z is equal to 0, and the above shear strain equation still applies in a plane strain. So, why I have brought this particular derivation is because you will see that wherever the problems are described, suddenly you will see that this 1 by 1 minus nu term comes, or 1 by 1 minus nu square terms will come in most of the fracture mechanics problems, but people just do not pay attention to this. It will come how? So, this is how it will be. If you just work it out, then you know that okay, so that is because we are manipulating the Young's modulus. The Young's modulus will have some different effect in the plane strain condition, and that is why we are doing this. So, that kind of alertness will be useful instead of simply looking at the expression what is given in the textbook. You can just derive by ourselves and then see and then get familiar with the terms. So, that is the purpose of this slide. Otherwise, there is no significance here. So, now in general, in a plane strain, you can write strain tensor like this: epsilon xx, epsilon yy, and epsilon xy, and normal strain and shear strain, normal stress and shear stress. So, please remember, in a plane strain condition, strain tensor is 2 by 2 matrix. For a plane strain condition, stress tensor is 3 by 3 matrix. Okay. So, you get this is not 0. So, this is very important, right. We will see when we discuss in a fracture mechanics concepts. So, it will be a dimple formation in a crack tip when very high stress is at the crack tip. So I will show some of examples when this kind of examples, practical examples when we discuss that subject. So this is a schematic for plane strain, and real-time examples are rolls in the roller bearings and dam section. They are all considered to be a plane strain condition. And what is plane stress? This is a schematic for a plane stress. Loading should be only in XY plane, and this is the stress tensor, and this is the strain tensor. Okay, so the stress tensor again, it is for a plane stress, it is 2 by 2 matrix, but not the strain tensor. Strain tensor is 3 by 3. So epsilon is not 0. So this is again a very important point to remember. Okay. So these are all the introduction to this stress strain relations. I just want to review, and these are all some of the fundamentals given in all the textbooks, but some of the subtle differences, small details, people don't pay attention, then they struggle to get the idea. So that's the idea. That's why I just wanted to review this, though it is simple. So I will stop here today. See, one important point is I have flipped the slides pretty fast, and if you start writing on the blackboard, it is always good. Okay, especially when I write too many equations on a slide, and that too if you just flip it through just by reading, it is very difficult to follow. So what I request all of you to do is, if you look at any of the expressions, you try to write, first you look at the video and then try to write of your own in your notes, and then see whether you are getting this expression by your own derivation. Small relations, but then you have to practice that. There is no other go, right? Even if I try to do it on the blackboard, and it will take a lot of time, but these are these important things you have to do. And if you have any difficulties, you can always write to us, and when we have the interaction section, we can get some of the clarifications, or you can send by email and so on. So I don't want to dump too much of information in every lecture as well. I want to go slow, but at the same time, I want to give enough background before I start the subject in detail. So I'll stop here. From next class onwards, I will do elastic anisotropic. Again, we are still in fundamentals. We are discussing the fundamentals. It will run through a few more classes before I cover other topics, which is required as a background for this course. So the next class I will discuss about anisotropy and elastic anisotropy, and then how the real-time crystal structures will have the elastic properties. Okay, so then we will slowly get into properties of materials and how the elastic deformation, and then we will be using all these concepts or terminologies, definitions, whatever we have used so far, and that will be useful. That's the purpose of these preliminary lectures in the beginning. So I will stop here, and then we'll continue in the next class.